we are discussing principles of laser. In the last lecture, we introduced the concept of coherency. We saw there are two types of coherencies in light. One is the temporal coherency and other one is the spatial coherency. And then we ask a question from optical communication point of view, why do we require coherency in light? And then we found that the temporal coherency is related to the spectral width of the source, whereas the spatial coherency is related to the beaming effect of the radiation coming from the source. Since for low dispersion on optical fibers, the spectral width has to be very small, we require high temporal coherency, and for high efficiency, since the radiation has to be launched inside an optical fiber, we require a very narrow beam of light, we require spatial coherency. So, we found that for optical communication directly the coherency is not required, but the parameters which are desirable for an optical source from communication point of view, they imply a high temporal coherency and high spatial coherency. And then we started investigating the principles of laser. So, we said if we take a simple material, consider a very simple system of two energy levels, and then you ask a question, what kind of processes the electron transition can have, and then we identified three processes which can take place inside the material. One is what is called the spontaneous process, other one is the absorption process, and third one is the stimulated process. We saw that if the electron is in excited state, then naturally it has a tendency to relax to the lower energy state, and in this process the energy difference is released in the form of a photon, and this transition probability is given by this parameter A21. Whereas, if the photon is incident on this system, then there are two possibilities. Either the photon can be absorbed by the material and the energy of the photon can be given to the electron, and which makes a transition upwards, or the photon can force an electron to make a downward transition and to emit another photon which is in complete coherency with the original photons. And these probabilities of transitions, upward transition and downward transition, were given by these constants B12 and B21. So, we saw that this constant A is the transition probability without the presence of a photon, and the parameter B essentially gives you transition probabilities which are related to the presence of a photon. These quantities A and B are called the Einstein's coefficient. In fact, this process, which is the stimulated process, that was the one which was postulated by Einstein, and we find that even if there is no direct evidence for this process to take place inside the material, it was proposed that if this process takes place, then essentially there are two downward processes which are taking place here, and there is a one upward process. So, with thermal equilibrium, these two processes must balance. So, then we wrote the equations for these two processes. So, for stimulated process, we said that the depletion rate of electrons at the higher energy level, that is given by A21 multiplied by N2, because the rate of change of electrons in higher energy level is proportional to the electron density at higher energy level. And then we got a solution of this equation, where the electron density as a function of time decreases exponentially at the higher energy level, and that time constant is what is called the spontaneous lifetime. Similar exercise we did for the other two processes, the absorption process and stimulated process, and here you said the rate of depletion of electrons in the lower energy state will be equal to this transition probability, which is given by this constant B12, but this process also depends upon the photon flux. So, this is the photon density rho f, and it is also proportional to the electron density at the lower energy state. Same thing we have written for the stimulated process, this minus dN2 by dt is equal to this probability, which is B21, again photon density multiplied by N2. And then we said if at thermal equilibrium, since the number of electrons at lower energy state and higher energy state are same, essentially the downward processes must be completely balanced by the upward processes. So, we got this equation that these two processes are downward processes, spontaneous emission, stimulated emission, and this is the upward process, which is the absorption process. Just by rearranging the terms, bringing all the row terms on one side and simplifying, we got the photon flux density expression, which was this. So, some rearrangement of the terms essentially says that the photon flux density is given by this expression A21 upon B21 divided by B12 upon B21 N1 upon N2 minus 1. Now, as we have seen that this ratio N1 upon N2, there is the ratio of the electron densities at the lower energy level and higher energy level. They are given by the Boltzmann distribution. So, N1 upon N2 is e to the power hf upon kT. So, we can substitute into this. So, we got photon flux density at thermal equilibrium, which is given by B12 upon B21 e to the power hf upon kT, that is N1 upon N2 from Boltzmann distribution minus 1. So, this simple exercise of balancing the three processes, the spontaneous process, the absorption process and the stimulated process, says that there is a net photon flux from this material, which is at temperature T, and the photon flux density is given by this expression here. What one can do next now, that we know that if you have a body at temperature T, then this body gives black body radiation. So, what we can say that whatever the photon flux density which we have got from balancing these three processes, this must be same as the photon flux density what we get from black body radiation, and this what precisely is done. So, if we get the expression for the black body radiation, the photon flux density which we get is given by this. So, this is your photon flux density as a function of frequency, that is related to this quantity n, which is the refractive index of the medium in which the radiation is coming. C is velocity of light, f is the frequency of radiation, and here hf is the photon energy and kT is the thermal energy. So, when these three processes were proposed, the black body radiation expression was well established. So, it was then straightforward to just compare these two expressions, one which is black body radiation expression, Rayleigh-Jean's law, and the expression which you have derived by balancing these three processes. So, if we compare now these two, you will see that this quantity here A21 upon B21 is this constant, So, we can write down just by comparison that we have A21 upon B21, that is equal to 8 pi n cube f cube upon c cube. So, essentially we get a relationship between A21, which is related to the spontaneous lifetime, and also this Einstein coefficient B21, which is the transition probability for downward transition from energy level 2 to energy level 1. The most important and striking thing which we see by comparison of these two expressions is that if I look at this quantity here now, which is 1 upon e to the power hf upon kt minus 1, and compare with this quantity, what we find is that B21 has to be equal to B12. So, the second thing which we see by comparison is B12 is equal to B21. So, we see here that B12 is equal to B21, and what is B12? B12 is the transition probability of electron going up, and B21 is the transition probability of electron coming down in the presence of a photon. And saying that B12 is equal to B21 says that these two transition probabilities are equal. That means the absorption process and the stimulated processes are equiprobable. Now, note here that the absorption process is always observed in life. If you go and search for any system where light beam is incident, it is always observed that the light beam attenuates as it travels inside the medium. So, the photons lose energy, there is the absorption of photons. We never find the stimulated process in nature, we always find only the absorption process in nature. But this simple analysis tells that these two processes are equiprobable processes, and that is a very profound conclusion, that one process which is always observed in nature and the other process which we never observe in nature are two equiprobable processes. One can then ask a question, why do we find the absorption very often in nature and we never find the stimulated emission in nature? And the answer essentially lies in the Boltzmann distribution, that although the probability of transition is equal, it depends upon where the electrons are. In thermal equilibrium, as we have seen, there are more electrons on the ground state and less electrons on the higher state. Even if photon has the equal probability of forcing a transition upward or downward, there will be always more transitions which will be going upward, because there are more electrons which are residing on the ground state. So, the net result we will always see is that there will be always more upward transition and loss of photon, which is the absorption process. So, what we find from this simple analysis is that the two processes, the absorption process and stimulated process, they are equiprobable processes. However, we always find the absorption process dominated in nature, and that is because we have more electrons in the lower energy state in thermal equilibrium, they are higher energy state. Naturally, then one can ask a question, if you could create a situation where there are more electrons on the higher energy state compared to the lower energy state, then what would happen? And the natural answer would be that now the stimulated process will dominate over the absorption process. So, if we want the stimulated process to dominate and to become more visible, then essentially we have to change the natural distribution of electrons in different energy levels. So, we have by some mechanism we have to transport more electrons to higher energy levels, and if there are more electrons at high energy level compared to lower energy level, then the downward process will be dominant over the upward process, and then the net effect will be stimulated emission. So, for seeing a stimulated emission, then essentially now we have to create a situation which is against the nature. So, we have to invert the population of the electrons, and that process is what is called the population inversion. So, by creating a population inversion, if the photon is incident on the medium, then you will have the coherent emission from the material. Though we can say that there is no net effect which is coming because of the stimulated emission, one can ask a question that radiation which is coming in the form of black body radiation, even that radiation is not of coherent nature, it is predominantly incoherent nature. So, we are having two processes which are essentially giving you the radiation out. One is the spontaneous process, other one is the stimulated process. The spontaneous process does not require a presence of a photon, whereas the stimulated process requires the presence of a photon. Going back to again the probability of these two being equal, one can now visualize this thing as follows. When we are now looking at the interaction of a photon with the system of energy levels, where difference is exactly equal to the energy of a photon, essentially we are talking about a resonant phenomena. The photon has an energy, that means it has a definite frequency. Similarly, the system has two energy levels and the energy difference is constant, which again is equivalent to certain frequency. So, we are having a characteristic frequency of the material, which is the energy difference divided by the Planck's constant, and we have a frequency of the photon. So, we are having now two systems. One is photon, which is having a frequency, and then we are having another system which is having a resonant frequency or characteristic frequency, which is equal to this photon frequency. And whenever we are having two systems which are having the same natural frequencies, there is exchange of power between these two systems. Precisely this is what is happening here, that since the frequencies of the photon energy level system is same, there now exchange of energy takes place between the photon and the material. Of course, which way the energy flow will take place will depend upon where the more energy is. So, if you are having more energy with the photon, then the energy will flow towards the system, and if it is the other way around, then the energy will go from the material to the photon. So, in natural process, thermal equilibrium process, the energy is with the photon, so it can impart the energy to material and electrons get excited, whereas if we go to the stimulated process, then there is more energy now with the material. So, energy is now imparted to photons, so you get more number of photons. So, essentially this phenomena is more like a force vibration phenomena, and whenever the force vibration takes place, essentially the photon which is getting emitted here is now completely under the influence of the original photon, and that is why the characteristics of these two photons are exactly identical. So, if by creating a mechanism by which the stimulated process dominates in the material, then we will get an emission which will be coherent in nature. One can do a very quick calculation to find out in a typical material, although these three processes are taking place, what is the contribution of the spontaneous emission over the stimulated emission. Now, as we have seen that the spontaneous process is proportional to P21 and the photon flux, whereas the sorry, this is the stimulated process. The spontaneous process is proportional to this quantity A21. So from the expression which we have got here, from here, if you simplify, you will get this B21 rho divided by A21. That will be nothing but 1 upon e to the power hf upon kT minus 1. And if you consider typical materials, the hf is much greater than kT. So if we consider, let us say, a radiation for lambda equal to 1 micrometer, for which the hf would be about 1.2 eV. This quantity hf upon kT would be 1.2 divided by 0.025, that is the thermal energy at room temperature. So this quantity here, e to the power hf upon kT, that will be of the order of e to the power 50. Or if you ask, at room temperature, if you look at a body, whatever radiation is coming out of it, the ratio of the stimulated emission to spontaneous emission is e to the power minus 50. That means the stimulated emission is practically non-existent at room temperature under thermal equilibrium. And that is the reason, although all the three processes are internally taking place inside the material, the net effect what we see from the black body radiation is an incoherent radiation, because for the typical energies which we are talking about, this quantity here, e to the power hf upon kT, is very large, and because of that, this ratio stimulated to spontaneous, that will be negligibly small. Having said that, now let us concentrate only on this process which is the stimulated process, or let us concentrate on these two processes which are taking place in the presence of the photon. Why we are saying that? That is because when this process starts, this process is a multiplicative process. One photon incident on this will give rise to two photons which are have same characteristic as original photon. If there are more electrons available here, then these two photons will pull down two electrons and will create two more new photons. So very quickly the photon number will increase, and as the photon number increases, more and more electrons will be pulled down and more photons will be released. So this process is rather a catastrophic process. It's a multiplicative process. Whereas if you look at this process here, which is the spontaneous process, then this process, naturally the electron is trying to come down. So you will see that the time constant of this is much larger than the time constant of this process. So whenever this process starts and starts dominating, this process does not have much chance to show, because as the photon number grows, very quickly the electrons will be pulled down. There will be hardly any chance of these electrons to show the spontaneous emission. So now onwards, whenever we discuss now the transitions, let us ignore this spontaneous emission. This we have already seen while discussing LEDs, and we concentrate only on these two processes, is the absorption process and the stimulated process. So now what we find is that if you wanted to have a stimulated emission, then you must have population inversion. That means there must be more electrons on the upper level compared to the lower level. One can now ask a very basic question. If I have to create population inversion, since naturally the electrons are going to be on the ground state here, by some mechanism I must transport the electrons to the upper level. By what is the mechanism by which I can transport the electrons? Again, I have to supply energy to this system, and the energy is given to the electrons, and the electrons are transported to the higher level. But again, when I am giving the energy to this system, the energy will be again given in the form of photons, and the energy has to be exactly equal to the difference in the energy levels. That means, for taking the electron from here to here, I must supply an energy or a photon which is having exactly the energy which is equal to the difference of these two energies. Now, if the energy is exactly same as difference of this, that means the frequency of the photon which is to be supplied for transporting electrons from this level to this level is same as what photon essentially we want to generate by the stimulated emission. Or in other words, what it means is, to get the stimulated emission out, which requires population inversion, I have to provide the photons to the system precisely at the same frequency. That means, these photons are temporally coherent, and these temporally coherent photons can transport electrons from lower level to higher level, which then are triggered by stimulated process will give the coherent emission out. Obviously, since for generating the coherent emission, I cannot have a coherent emission in advance, simple two energy level system will not work. However, what one can note here is that when the energy is supplied in the form of this photon for transporting electrons from here for creating population inversion, these photons need not be spatially coherent. So, they must be coming from various directions. Only if they are temporally coherent, then they can supply the energy which is exactly equal to this difference, and electrons can be transported from here to here. So, in practice, then it appears that a simple two energy level system, what we have discussed up till now, cannot provide a population inversion, because it will require coherent emission to create that, and therefore, a laser cannot be created. So, what is done is then that you create essentially the system which are more energy level systems. So, let us say we have energy level here, these are our energy level, and let us say this is the energy level which is E1, this is the energy level E2. And then what we do is we identify the material which have other energy levels here, which are not as discrete as these energy levels, and you are having essentially a band of energies where electron can be transported. Now, since you are having a finite energy width here, by providing temporally incoherent radiation corresponding to this energy width, electrons can be transported from the ground state to this state. So, let us say this energy level is having energy denoted by E3. So, now the process is as follows. The electron is transported from the ground state to this upper state, energy state. And then, if the lifetime of the electron to relax from this level to this level is much smaller, then the electron will be transported to this level, and very quickly, because of the spontaneous process, this electron will relax to this level. So, the electron will come from here to here, and it will come to second level. So, if I say the energy level 1, 2, 3, they have different time constants, spontaneous time constants associated with them. So, let us say this time constant is tau 3, 2. That means the relaxation time from level 3 to level 2. And if this time constant is much smaller compared to the time constant corresponding to energy level 2 and 1. So, if it is much smaller compared to tau 2, 1, then as the energy is supplied to this system corresponding to this energy difference, E3 minus E1. The electrons will be transported to this level. Very quickly the electrons will come here to energy level E2. And now since tau 21 is much larger compared to tau 32, it will wait there at energy level 2. Then if the photon is incident now with an energy difference which is E2 minus E1, then this electron will be pulled down and we get the stimulated emission out from this system corresponding to the energy difference E2 and E1. So what it appears now that to create a laser, we require at least a 3 energy level system, out of which one energy level has to be fairly broad so that electrons can be excited to that energy level by using incoherent photons, and then these electrons will decay to another energy level, and then actually the lasing action or stimulated action will take place between these two energy levels. So the triggering photon will have a frequency corresponding to E2 minus E1. So in principle, then it looks like in practice a 3 energy level system will be the minimal system which will require for creating the population inversion. However, you will see that even the 3 level system will not work very efficiently in practice, and the reason is very simple. Even if the electrons are accumulated now at this region here, when this photon comes, as we saw that the probability of interaction of this photon with this electrons or this electron is equal. That means when this photon comes, either the photon can pull down this electron to emit another stimulated photon, or it can pull an electron up from the down state to this state and the photon may get lost. And as we have seen, to see the net stimulated process taking place, the number of electrons in the upper level have to be larger compared to the number of electrons here, which is what is called the population inversion. So what that means is that total number of electrons which are there on ground state, more than half of those electrons have to be transported to this level. Then and then only one can see the net stimulated emission from the system. If you do a quick calculation that a very huge number of electrons which are present on the ground state, and if they were to be transported to the upper level, a huge amount of energy is to be supplied to the system to get a very tiny stimulated emission coming out of this. So again you will see that in principle, though the 3 level system can create the stimulated emission, it will not be very efficient because it will require a huge amount of energy to be supplied so that more than half the electrons are transported to the upper level. So what one can do, one can essentially create one more level here, and now we call this is truly the ground state. So let us say this is the energy level 0, and instead of transporting now electron from this to this, the electron is transported from here to there, to this level. So this is the ground state. From here the energy is supplied now corresponding to the difference which is E3 minus E0, and this band is broad. So this is the incoherent photon flux which is incident on this, which is exciting the electrons. The electrons go from here to here. Since this time is much smaller compared to tau 2, it will relax to this. It will wait because this time is much larger compared to this time. However, if I want to have a population inversion between these two levels, what we must guarantee is that after the electron has made a transition due to this process, it should not wait here in this level, because if it waits in this level, then again you have a similar problem that you will have more number of electrons which are here. So what we should have the time constant between these two levels now has to be much smaller again compared to this time constant. So, electron again will make a transition from here to this level by this time constant, which is tau 10, and tau 10 has to be much less again than tau 21. This has now created essentially a 4-level system, energy level system, where even a small number of electrons can be transported to this level, and if this level is cleared very quickly, even the small number of electrons can create population inversion between these two levels. So, if you want to have an efficient system which can work in practice, at least a 4 energy level system probably is required with appropriate time constants of transition between different levels, and then only the stimulated emission can take place. We will see that later on when we see various laser systems, that actually the material which are used for lasers, they have a fairly complicated energy level system, and appropriate energy bands are chosen so that we have appropriate time constants which will create population inversion, and then we have a lasing action between those two energy levels. So, a 4 level system or more than 4 level system probably is more appropriate for creating the coherent emission from a atomic system with good efficiency. Let us now go back to our original thing with this understanding that by doing these mechanisms, we have created the population inversion, and then we have a certain number of electrons which are in the upper level, and there are certain number of electrons which are at the lower level. And then when the photon is incident, now with equal probability either upward transition will take place or downward transition will take place. And as we mentioned, since this process is a very fast process, the spontaneous emission will not have any chance to show. So, in now our discussion, let us assume that the spontaneous emission is negligible, and essentially these two processes are only the one which are taking part. If we do this now, then our equation of the transitions of electrons, the net downward transition, if you want to write, we can get the net downward transitions, which will be net downward transitions, which will be minus dN2 by dt, that will be equal to B21 rho of f into N2. These are downward transition minus the upward transition, which will be B12 rho of f into N1. And as we have shown, B21 and B12 are equal. So, this thing essentially can be written as B21 rho of f into N2 minus N1. So, if N2 is greater than N1, which is the population inversion, then there will be more downward transitions. If N1 is greater than N2, then there will be more upward transitions. So, in normal situation, N1 will be more than N2. So, you will have more upward transition, which is absorption process. And for population inversion, N2 will be more than N1. So, there will be net stimulated emission process. Now, each transition which is going to take place, which is downwards, is going to give one photon out. So, if I say that the number of photons are given by NP, then the downward transition rate of electrons, that will be equal to the photon generation rate. So, that means minus dN2 by dt, that will be equal to d n photons divided by dt. So, this equation what we have here, we can get d n p by dt, that is equal to B21 rho of f into N2 minus N1. This is the rate of photons. If I multiply this quantity by the energy of photons, which is h into f, then this quantity essentially will tell us the energy per unit time in the form of photons. So, if I say that this quantity here multiplied by h f d and p by dt, which we can write as d by dt of h of f into np. But this quantity is nothing but the photon flux density, which is nothing but this quantity rho of f. So, you have this quantity is rho of f. So, now we got a very nice relationship that the rate of change of this photon flux from the system will be equal to B21 rho of f into N2 minus N1. So, we got the equation for the photon flux from the system, which is d rho by dt is a function of frequency, that is equal to B21 rho of f into N2 minus N1. Knowing the relation between P21 and A21, and A21 is 1 upon the spontaneous lifetime. If you go back and get those expressions as we derive from comparing the black body radiation and the Planck's constant, then we can get for B21 expression, and this expression essentially would become C cube h of f divided by 8 pi f cube n cube tau spontaneous into rho of f into N2 minus N1. So, now we are seeing that the photon flux varies as a function of time, and that is given by this differential equation. But when we look at the photons essentially is an electromagnetic wave. So, photon is not going to be staying at a particular point as a function of time, it moves with velocity of light. That means, as the photon flux is growing as a function of time, the photon is also moving in space. And we know that the x distance traveled by the photon is equal to the velocity of light, which is c by n into t. So, we can write from here that dx is equal to c by n into dt. So, I can get here 1 by dt from here, that is equal to C by n to 1 by dx. So, now we can change this equation, which is a differential equation as a function of time to as a function of space. So, we can write this quantity here, which is d rho f of dx into dx by dt, which is C by n, that is equal to this quantity here. So, C cube h of f divided by 8 pi f cube n cube tau spontaneous rho of f into n2 minus n1. 1 C by n will cancel with that, and then finally we get the equation for the photon flux as a function of distance, which will be d rho of f by dx, that will be c square h upon 8 pi f square n square tau spontaneous into n2 minus n1 into rho of f. So, if we define this quantity, this one here, by some quantity g, which is a function of frequency, then this equation can be written as d rho of f by dx, which is equal to g into rho of f. And the solution of this equation would be rho of f as a function of x, that will be equal to rho of f at x equal to 0 into e to the power g of x. So, this quantity then we can call as the gain constant of the system, and the photon flux will grow exponentially as it travels inside the material with this gain constant. And as we see, the gain constant depends upon various parameters. It depends upon the frequency, it depends upon the refractive index of the medium, it depends upon the spontaneous lifetime. But more importantly, this quantity is directly proportional to this difference n2 minus n1. And if n2 is greater than n1, then g is positive. If n2 is less than n1, then this quantity is negative, and when n2 is equal to n1, that time this quantity is 0. So, essentially we have now these three things possible. One is if n2 is less than n1, which is the normal condition, then g is negative, or it represents exponential decay of this function. So, g is equal to minus alpha, where this quantity is the attenuation constant. So, if I have a normal situation, then there is the exponential loss and energy will decay exponentially by the attenuation constant alpha. If n2 is equal to n1, then g is equal to 0, and then we call this thing as the transparency condition. That means the photon flux neither grows nor decays as it travels inside the material. Third possibility is if N2 is greater than N1, which is population inversion, then G is positive and you have a growth of the photon flux. So, we see that now quantitatively, whenever we have a population inversion, then the photon flux is going to grow exponentially inside the material as it travels. So, now if we want to really grow the stimulated emission inside the material, if the radiation travels more and more inside the material and if the population inversion is there, then the radiation will keep growing. So, now the idea is essentially to make the radiation travel more and more inside the material by a certain mechanism, maintain the population inversion, and if we do that, then we get the stimulated emission coming out of the system, which is the coherent radiation. So, this is the fundamental now equation for the laser. When we meet in the next lecture, we will try to see these characteristics that this gain constant depends upon and what it means really for the lasing action. And then we will also go and ask the questions that even if the stimulated emission is internally created inside the matter, would it be externally visible, and how do we make this radiation coherent, which we are essentially looking for.